Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 9th, 2026, just about 3 days ago. It introduces a new training method called Citation-Aware Group Relative Policy Optimization, which boosts search agent performance by up to 8 points, while preventing models from taking reasoning shortcuts. The paper is titled, Chaining the Evidence, Robust Reinforcement Learning for Deep Search Agents with Citation-Aware Rubric Rewards. And as we'll see later, the results for reducing hallucinations are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the central problem with standard reinforcement learning methods. At the top, we see a complex multi-hop question about a meteor event and a Scottish engineer. The agent performs a few search actions and generates the final response shown in the middle panel. Notice the text highlighted in red, which marks ignored hops or reasoning shortcuts the agent took. Despite skipping these critical logic steps, the bottom section shows the agent still receives a perfect outcome reward of 1, simply because the final answer, 66 tons, happens to be correct. So, Figure 2 details the solution, starting with rubric initialization on the left. Here, the system decomposes the complex question into atomic, verifiable facts called rubrics. The middle panel then tracks the reward computation, where the model must identify hidden entities and back them up with valid citations. A key step is the evidence connectivity check, shown in the top right, which builds a graph to ensure these facts form a logical chain. Finally, the bottom section illustrates C-GRPO, which combines this granular rubric score with the final outcome to train the agent. Alright, Table 1 presents the main experimental results across 4 challenging benchmarks, including BrowseComp, XBench Deep Search, and GIIA. The top sections list strong baselines like OpenAI 03 and DeepSeek version 3.1 for context. The real test, however, is in the bottom section, labeled Our Agents. Here, the authors evaluate both 4 billion and 30 billion parameter models. You can see that C-GRPO, the last row in each block, consistently achieves the highest scores. For the 30 billion parameter model at a 128K context budget, it significantly improves upon standard GRPO, showing that the citation-aware rewards lead to better generalization. So, Figure 3 breaks down these advantages further. The bar chart on the left tracks accuracy improvements over the supervised baseline. Here, the blue bars for C-GRPO consistently beat the orange standard GRPO bars, gaining over 12% on the XBench benchmark. Then, the other 2 panels demonstrate test time scaling. In the middle graph, the blue line keeps climbing as the context budget increases, even extending beyond the 64K training limit marked by the green dashed line. Similarly, the right plot shows that allowing more tool call steps translates directly into higher accuracy. Well, Table 3 shifts the focus to open-ended research tasks using the Deep Research Bench. The columns here evaluate agents on specific qualities like comprehensiveness, insight, and readability. At the top, we see benchmarks for proprietary systems, such as OpenAI Deep Research and Grok. In the bottom section, specifically the 30 billion parameter model, C-GRPO achieves an overall score of roughly 42. This result is particularly strong because it surpasses proprietary baselines like Tongyi and Grok, proving that the citation-aware rewards help the model generalize to complex PhD-level reporting tasks. Finally, Table 5 validates the specific design choices through an ablation study. The top row establishes the baseline performance of the full Deep Dive 4B model. Beneath it, we see significant drops when key components are removed. For example, looking at the third row, removing the evidence connectivity check causes the GAIA score to fall from 50 down to 44, which proves that verifying the logical chain is crucial. The last row shows the biggest drop, occurring when rubric rewards are applied to all rollouts instead of just the correct ones, confirming that rewarding incorrect reasoning paths simply confuses the model. Ultimately, this work drives home 2 main points. Getting the final answer right isn't enough if the reasoning is flawed. By enforcing step-by-step evidence verification, we can stop models from taking shortcuts. Also, the results show that fine-grained process rewards are key to building search agents that are both accurate and trustworthy. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.